These are the notes for AP Calculus on the topic of approximating definite integrals using Riemann sums and trapezoidal sums. So let's first take a look at approximating using Riemann sums. And there's three different types of Riemann sums, and they all involve rectangles. So just think Riemann and rectangles both start with the letter R, so it's easy to remember. That's the shape we're going to be using. And remember, what a definite integral represents is the exact area under the curve on whatever interval the lower and upper limit represents. So let's first look at what's referred to as the right Riemann sum. So the graph of the function f is shown below, so that's what we have right here. Approximate this definite integral from -2 to 4, f of x dx, using a right Riemann sum. Okay. So again, remember what this represents exactly is the area under the curve between the curve and the x-axis here. But notice this one, we don't have the actual equation of the function, so we can't integrate it by hand, and we also don't, this is not just made up of geometric shapes, so you can't just use geometry to find that area. That's why we have these approximation methods. So it says 3 subintervals of equal length. Sometimes the subintervals are going to be equal, sometimes they won't. This one they are. And then we're also going to sketch the graph of the right Riemann sum to show how we're approximating using these rectangles. So if you have equal subintervals, to calculate the width of equal subintervals, pretty simple formula that you use here. You just, let's put it in words here for what it is first, then we'll put the actual numbers in. Here you want the width, first start with the width of the interval. And then, that's the width of the limit, just divided by the number of subintervals, since they're all equal. And we'll see later on, sometimes subintervals are not equal width, but this time they are. Okay. So to get the width of the entire interval, you just use your upper and lower limits here. And start with the upper limit, 4, and subtract whatever the lower limit is, in this case, -2. That'll tell you the width of the whole interval. And then divided by, in this case, we've got 3 subintervals of equal length, so we divide it by 3. That gives you 6 divided by 3, which is 2. So now we know 2 is the width of each of these equal subintervals. And as soon as you know the width, that allows you to draw the number limit. We're starting at -2, the lower limit. And now that we know the width is 2, we can go by 2s. So if you add 2 to -2, then you're at 0. Add 2 more, you're at 2. Add 2 more, you're at 4. So you can see there's our 3 subintervals, unless we ended at the upper limit, of equal width. They each have a width of 2. So let's draw and see what that looks like. Remember, these are going to be rectangles we're using to approximate the area of this curve. Now with the right Riemann sum, it just means we use the right endpoint on each of these subintervals to get the height. So on the subinterval from -2 to 0, well, the right endpoint on the right end is at 0. So we look at our graph, where's the function at 0? Well, it's right there. And use that to draw our rectangle. Choose a bit color, so it shows it better. Right in there. So that's going to be our first rectangle. Then the next subinterval is from 0 to 2. The right endpoint on that subinterval is 2, so look where the function is at 2 right here. And use that to figure out, that gives you the height of the rectangle on that subinterval from 0 to 2. And finally, the last subinterval here is from 2 to 4. The right endpoint's at 4. But notice that on the graph at 4, that gives you the height of the rectangle, but look at what happens. We basically have a rectangle that has no height. It's flat there. So, in general, what we're doing to get the area of each of these rectangles, we're just taking the width, I'll call it W sub 1, times the height, I'll call it H sub 1, of the first rectangle in the subinterval from -2 to 0, plus the width times the height of the second rectangle, plus the width times the height of the third rectangle. So the width we know in all of these is 2, we already figured that out. And the height in general comes from the right endpoint, since this is the right Riemann sum. So the right endpoint, remember, on this subinterval was 0, so it comes from the y-coordinate there, in other words, f of 0. That'll give you the area of this first rectangle, plus 2 times the right endpoint on this subinterval is a 2, so f of 2, plus 2 times the right endpoint on this subinterval is a 4. So f of 4. Now write it this way so you can see where everything comes from. I know on the graph, in this case, you can easily tell what these are. So now let's look at f of 0 with a y-coordinate 0. F of 0 is 1. So the height is 1. Plus 2 times f of 2 was right here at 5. F of 2 is 5. So 2 times 5. Plus 2 times f of 4, well, that was 0. So now we can calculate this out. The area of the first rectangle, 2 times 1 is 2, plus the area of the second rectangle, 2 times 5, the area of 10, plus the area of the third rectangle, 2 times 0, it's like a flat rectangle, is 0. Add those up gives you an area of 12. So that's our approximation using 3 subintervals of equal length using a right Riemann sum of the area of the curve. Now we can take a look at this and see how good of an approximation do we think this is. And does it overestimate or underestimate? Well, let's take a look at this first subinterval from 0 to 2. We can see this rectangle here definitely underestimates, and this is this whole section right here, the actual area of the curve. However, on the second subinterval from 0 to 2, this time this rectangle overestimates the area because it's got all this extra area here that's not really under the curve. And then finally, on the last subinterval, obviously, since there's no area enclosed in that rectangle, it has a height of 0, it underestimates it because it misses the entire area there. So it looks like overall, probably underestimates. So 12 is probably too small for the actual definite 12 on this particular graph. But again, it's going to depend on the graph and the function, whether these overestimate or underestimate. And we'll look at some of the causes of that in a little bit. All right, so there's the right Riemann sum. Now let's take a look at the left Riemann sum. Well, it's the same idea. We're still going to use 3 subintervals of equal length. So again, the width of each subinterval is going to be 2. Let's draw our number line again so we can see where everything's coming from though. Again, we're using equal width here. So it's just -2 to 0, 0 to 2, and 2 to 4. There's our 3 subintervals for the whole interval from -2 to 4. Now let's draw it first on the graph. But this time, as the name suggests, it's a left Riemann sum, meaning instead of using the right endpoint to get the height of the rectangle, we use the left endpoint on each subinterval. So the left endpoint on -2 to 0 is -2. So look where the function is at -2. It's right there. And we use that to draw a rectangle. Oops. To get the height of that first rectangle. Now the next subinterval, from 0 to 2, the left endpoint is at 0. So, right there is where the function is at 0. So from 0 to 2, that's going to give us the height of the second rectangle using the left Riemann sum from 0 to 2. And finally, from the subinterval 2 to 4, the left endpoint's at 2. So if we look at 2 right there, that's going to give us the height of our third and final rectangle on the subinterval from 2 to 4. So this time, these are the rectangles we use using a left Riemann sum to approximate the area of the curve. So again, we know the width. What we're going to do is, since these are rectangles, just take the width times the height of the first rectangle plus the width times the height of the second rectangle plus the width times the height of the third rectangle. And we know the widths are all 2 again. So let's look at where the heights are coming from. This time they're coming from the left endpoints of each subinterval. So again, the left endpoint of the first subinterval was -2, so that's f of -2. Plus the width again of all these, since they're equal, second subinterval is 2. This time the height, the left endpoint is 0 on the subinterval from 0 to 2, so f of 0 plus 2 times the left endpoint on this subinterval is at 2, so f of 2. So we have 2 times f of -2, and c is up here at 5, plus 2 times f of 0 is right here at 1, it's the height of our second rectangle, plus 2 times f of 2, it's right here at 5, is the height of our third and final rectangle. So 2 times 5, the area of the first rectangle is 10, plus 2 times 1, the area of the second rectangle is 2, plus 2 times 5, the area of the third rectangle is 10. Add those up gives you 22. Is our approximation for this definitional for the area under the curve. So let's take a look and see whether you think this overestimates or underestimates. Well, in this section you can see it overestimates by this much, on -2 to 0, but on 0 to 2 it underestimates by this section here. And then 2 to 4 overestimates by this much. So looks like this one might be overestimated overall. So if we were right about that, 22 overestimates and 12 underestimates. So we know the actual answer is somewhere between 12 and 22. But that's still a pretty big range. And again, it just depends on the graph and the subintervals you're using to determine whether it overestimates or underestimates. There's one third and final Riemann sum that's also rectangles, and that's referred to as the midpoint Riemann sum. So again, let's draw our number line. We're going to still use 3 subintervals of equal length, but this time using the midpoint Riemann sum. So let's draw our number line now. We still have the same 3 subintervals, -2 to 0, 0 to 2, and 2 to 4. Let's draw this one here, but this one, what we're going to use is the midpoint of each subinterval to get the height of the rectangle, rather than the left endpoint or the right endpoint, as we saw in the previous 2 methods. The midpoint is really just the average of the 2 endpoints. So if you take -2 plus 0, that's -2 divided by 2 is -1. Well, in this case, it's kind of obvious that's the midpoint. But if you had some weird numbers, that's how you find it. So -1, let's find where the function is right there. Right there. This one's probably the trickiest to draw because you have to go both directions when you're drawing the rectangle there. That gives you the height of the rectangle on the first subinterval from -2 to 0. Oops. There we go. Then the midpoint on the second subinterval from 0 to 2, the midpoint of that is 1. So let's find where the function is 1. Now it's going to give us the height of the second rectangle right there. And finally, the midpoint of the third subinterval from 2 to 4 is 3. So let's find where the function is at 3, right there. Now that'll give us the height of our third and final rectangle. So those are the three rectangles using the midpoint Riemann sum. So again, they're still rectangles, so we're still doing width times height plus width times, width times height plus width times height of each of the rectangles. And again, the widths, we already figured out each subinterval is 2 in this case. F of this time, the height comes from the midpoint, f of -1. Plus 2 is the width, and the midpoint of the second subinterval was f of 1. Plus 2 times the height comes from the midpoint of the third subinterval, which is at 3, so f of 3. And using the graph here, we can actually tell what these values are. F of -1, that's 2, the height of our first rectangle, plus f of 1, right here is a 3, plus 2 times f of 3 is at 4. So 2 times 2 is 4, there in the first rectangle, plus 2 times 3 is 6, plus 2 times 4 is 8. Add those up gives you 18 as an approximation. So on this one, it's a little hard to tell whether it under or overestimates. You can see this rectangle underestimates this section, but it overestimates this. So it bounces out a little bit. This one underestimates this part, overestimates this part, but underestimates this part. And this one underestimates this part and overestimates this. So this looks like it might be a fairly decent approximation. We're pretty close of 18. All right, now let's take a look at the fourth method of approximation. This is the only one that's not rectangles. As the name suggests, it's not referred to as a Riemann sum. It's referred to as a trapezoidal sum. Okay. And we're still approximating the same definite interval, so that's not changing. But let's just review how we find the area of a trapezoid. It's a little more complicated than just width times height, but it's not super complicated either. So if we have a trapezoid like this, this is what our trapezoids are typically look like, something like this. We've got some width to it here, which we'll calculate. And then we've got two different heights. The ones that run parallel, we'll call them h sub 1 and h sub 2. So really what we're doing is we're adapting the formula for the area of a rectangle. It's just we have to average these two in order to calculate the area, because they're different. So we're sides that are parallel. So averaging them, you add them up and divide by 2, but I'm going to write that as times 1/2. Okay. And you can multiply by the width, but it's actually easier if you have that in front of the parentheses, so we're going to write it like this. 1/2 W times h sub 1 plus h sub 2. So that's how we'll calculate the area of each of these trapezoids. So we still have the same three. This time we're using the trapezoidal sum. The same three subintervals of equal length. So we'll draw our same number line, but we'll use it a little differently. -2 to 0, 0 to 2, 2 to 4. And again, we're going to sketch the graph of the trapezoidal sum. So this time, when you draw the trapezoid, you actually use both the left and right endpoints to form the trapezoid. So you use the -2 and the 0 on the first subinterval. -2 is right here, 0 is right there, and then just line up your ruler there and draw a straight line that connects the two endpoints. And then draw vertical lines that head down from those endpoints to form our first trapezoid. Then the next trapezoid from 0 to 2, connect the endpoints at 0 and 2. We already have the endpoint at 0. The endpoint at 2 is right there. And again, draw a straight line that connects those two. And then 2 to 4. And we already have the endpoint at 2 right here. Endpoint at 4 is right here. And draw a straight, whoops, I forgot to draw the vertical line down on this trapezoid here. And we'll draw that connects those endpoints and draw the vertical lines down, but notice this one actually looks like a triangle, not a trapezoid. And that's okay, we'll see why that's still okay with the formula. Okay, so let's calculate each of these separately. Now we know on all of them, we're going to use the 1/2 times the width. That's h sub 1 plus h sub 2. So let's calculate that for the first trapezoid. The 1/2, we know the width of each of these is 2. And the heights come from both endpoints, right? So f of -2 plus f of 0. That'll give us the area of the first trapezoid. Then 1/2 times the width is 2. And the heights in the second trapezoid come from f of 0 and f of 2. And then the area of the last trapezoid would be 1/2 times 2. And the heights from the endpoints come from f of 2 and f of 4. Now in this case, because the width is 2, you can see what happens that all these 1/2s from the 2 reduce out. That won't always happen, but when the width is 2, it does. And so we're just left with the sum of the heights. F of -2, we can see it's 5, plus f of 0 is 1. So the area of our first trapezoid is 6. And then f of 0 we know is 1, plus f of 2 is 5. There's the second trapezoid, also 6. You can see why that is. These are just mirror reflections of each other. And then f of 2 is 5, plus f of 4 is 0. So you can see the area of this one would just be 5. And let's see why it's okay. We use the trapezoid formula, but wait, how can we do that when this is a triangle? Well, take a look at the formula here. What really happened is the second height is 0, right? So that's like having h sub 2 is 0. And if we cover that up, look at what's left if we just have this. 1/2 width times height. Well, if you just look at that part, doesn't that look like the area of the triangle, 1/2 base times height? Because it is. So that's why when this height 2 is 0, when we use the trapezoid formula, it really turns into the area of a triangle. So it still gives us the right answer for the area, even when this triangle kind of degenerates into a, even the trapezoid degenerates into a triangle. So then add up all these areas, gives you 17 as our approximation. And you can see on this one, the trapezoid overestimates by this much on this first subinterval. Here it overestimates this, but underestimates this, so it kind of balances it out here. And this one it underestimates, and this is this whole section right here. So again, this looks like a fairly decent approximation, close to the last one, which was 18. But again, it depends on the graph, which one of these approximation methods will be the most accurate. In this case, it probably looks like either the trapezoidal sum or the midpoint Riemann sum is the most accurate, but that's not always going to be the case. Now, notice here we just use 3 subintervals. But in reality, what's happening with this definite interval, the reason why it's the exact area, remember, is because as you use more and more subintervals, these approximations, as you might guess, become more and more accurate. And to get it exactly right, remember dx represents a width that's infinitely thin. So that means we're using an infinite number of rectangles, which gives you the exact area using calculus. But you can only do that again if you have either the equation of the graph or these are just geometric shapes. Otherwise, we just have to do our best approximation if we don't have the equation of the graph, or they're not just made of geometric shapes. The next thing we're going to investigate is for the left and right Riemann sums and the trapezoidal sums. Let's figure out what causes these methods to either overestimate or underestimate the definite interval. So what we're going to do on each of these, you can see we've got the same graph here. And on this graph, we're going to look at these 3 methods. We're going to draw them here and then determine based on our drawing whether they overestimate or underestimate the definite interval. So just pick some interval from A to B. I'll just write A to B on this because it's from A to B here. And for the left Riemann sum, we're going to use the left endpoint to draw our rectangle. So you really could use any number of subintervals, and it's going to give you the same answer. But the easiest to draw is just actually one subinterval, just using the whole interval. So you can see it's missing this whole section right here, so it's underestimating, because remember what the definite integral here represents. From A to B, this is the exact area between the curve and the x-axis. So that'd be right here, all this area right here. That's the exact area. And you can see this rectangle is definitely missing this whole section here, so it's underestimated. So in this particular graph, the left Riemann sum underestimates its definite integral, so we can say it's less than. All right, let's take a look at the right Riemann sum. See if that's the same or if it's different. So again, we just pick some interval from A to B. But this time to draw a rectangle, we'll use the right Riemann sum, so the height of the rectangle is going to come from the right endpoint. Again, we're just going to use one subinterval to make it easier to draw. The right endpoint to draw a rectangle. And the right Riemann sum, you can see it overestimates it, this whole section right here, the area of the curve, which is the definite integral. So this time the right Riemann sum would be greater than the exact area with the definite integral. Overestimates. And then the trapezoidal sum, remember how we draw this. Here, remember, you actually connect the endpoints. And definitely use a ruler on this, otherwise it might be hard to tell on this one. From A to B. And line up your ruler there to draw a perfectly straight line between those two endpoints. You just do that. Okay. And then you draw the trapezoid that's formed there. If you draw it perfectly straight using a ruler, you can see, well, it misses that little tiny section right in there. So it does underestimate the exact area by just a little bit. So we'd say this is less than. Definitely. Notice the one we're leaving out here is the midpoint Riemann sum. And that's because that one is the hardest to determine just by the graph, or the shape of the graph, whether it underestimates or overestimates. So we're not going to consider that one. But the other three you can tell. All right, so that's one way a graph can look like. Let's take a look at, basically, other than just being a straight line, in which case we wouldn't need to approximate, it would just be a geometric shape. If it's curved, the 4 different ways the graph can look, and look at the 3 different methods here. See if they underestimate or overestimate, and then we'll figure out what the causes are. So another way the graph could look is like this. So again, we've got some interval from A to B. Let's use the left Riemann sum. So use the left endpoint at A. Let's draw our rectangle. It's a Riemann sum in there. You see this overestimates by this whole section right here. So that's going to be greater than the actual area. The right Riemann sum. Using the right endpoint here, this graph, to draw the height of a rectangle. See, this time it misses this whole section right here, so it underestimates, so it actually be less than the exact area the definite integral represents. And then the trapezoidal sum. Again, here's where you connect the two. Once again, use a ruler. You can draw a perfectly straight line. It's easier to tell. See, this one misses this little section right in here, so it underestimates, so it's less than. All right, let's take a look at two more ways to graph the book. Okay, let's look at this one on the left. Let's again start with the left Riemann sum. Using the left endpoint at A, draw our rectangle in there. Using the height of the rectangle, using the left endpoint. Let's see, it overestimates by this much, so this is greater than the definitional. Then the right Riemann sum. Using the right endpoint. Get the height of a rectangle. See, now this is this whole section here. So that underestimates, so that's less than the definitional. And then the trapezoidal sum. Use a ruler here to draw a perfectly straight line that goes between the two endpoints. Trapezoid. You can see this time it overestimates the area by that little section. So that'd be greater than the exact area represented by the definitional. All right, so go the fourth and final way with these three methods, whether they overestimate or underestimate. So here from A to B, the left Riemann sum, we use the left endpoint to draw the height of a rectangle. See on this one, it's missing this whole section right in here. So it's definitely underestimated, so that's less than the definitional. Then the right Riemann sum, using the right endpoint. Definitely overestimates this whole section right in here. So it's greater than the definitional. And then the trapezoidal sum, you have to connect the two endpoints. Straight line using a ruler there. See, that overestimates by that little section right in there. So that's greater than the definitional exact area. All right, so this is a way you can actually figure it out if you forget which way it goes. Just draw yourself a picture of what it looks like to see if it underestimates or overestimates. Now let's see what the causes are, though, if you have to justify why it does. So let's start with the left Riemann sum. It over-approximates the definitional when, all right, let's see when that happens. All right, well, let's look at the leftmost column. It over-approximates, not in this one. This it over-approximates, and this one. So what does this graph, the second graph, and the third graph, what do these two have in common? Well, if you look at them, both of them are decreasing, right, as we go from left to right. And that's what causes the left to overestimate. And when a graph decreases, that's because the first derivative is negative or less than 0. So this is being when f prime of x is less than 0. Or another way to think about f is decreasing. And now let's look at when the left Riemann sum under-approximates. Well, that's this graph here, the fourth graph that under approximates, and the first graph. So what does this first graph and the fourth graph have in common? Well, these two functions both are increasing. So that's caused when the first derivative is greater than 0. That's when f is increasing. Remember that always refers to left order. Now let's look at the right Riemann sum. When does that over approximate? Let's look at our middle column now. So it did over approximate on this one, and it also over approximated on the first graph. So what does the first graph and fourth graph again have in common? Notice they're both increasing. So when f prime of x is greater than 0, f is increasing. And when did the right Riemann sum under approximate? Well, that was on the third graph here and the second graph. And what do these two graphs have in common? Well, again, on both of these, the function is decreasing, which is caused by the first derivative being negative or less than 0. So f prime of x is less than 0, and f is decreasing. So notice it's reversed for the left and right Riemann sums based on its increasing or decreasing. That's because depending on if the graph is increasing or decreasing will determine whether the left or right endpoint, which one is above the graph and which one is below the graph. Well, let's see if it's the same or a different cause for the trapezoidal sum. Over approximates. Well, that would be this graph. Let's look at our third column here. And this graph. Well, notice this one, the third graph is decreasing. This graph is increasing. So it can't be the same cause as our left and right Riemann sum. But there is something these two graphs have in common. If you take a look at the third and fourth graph, notice the shape of the graph here. Both of these are concave up, shaped like a cup. And that's caused when the second derivative is greater than 0. So when f double prime of x is greater than 0, this f is concave up. And let's look at when the trapezoidal sum under approximates. Well, that would be this second graph and the first graph. Again, notice it can't be increasing or decreasing because this one's increasing. First graph and the second graph is decreasing. But notice what these two graphs do have in common. They're both concave down, shaped like a frown. So that's what's causing the trapezoidal sum to under approximate. And this is concave down when f double prime of x, the second derivative, is less than 0. So whenever you're asked to justify whether any of these three methods, overestimate or underestimate the graph, the definite integral, for the left and right Riemann sum, it's based on the first derivative, whether the function is increasing or decreasing. But for the trapezoidal sum, it's based on the second derivative, whether the graph is concave up or concave down. All right, now let's take a look at some applied problems where you usually see these, where you have a table of values and you don't have the graph or the function itself. All right, so this one says a school carnival sold raffle tickets as a fundraiser between noon, which is defined as time 0, and 8 p.m., which is defined as time 8. The number of raffle tickets sold t hours after noon is modeled by a differentiable function r from 0 to 8. R double prime of t is less than 0 for all t. Values of r of t, in the table notes it also says in hundreds of tickets at various times t are shown in the table. So it's part A, it says use the trapezoidal sum with the 4 subintervals given by the table. So notice on here, the 4 subintervals given by the table here, from 0 to 8, we're going to approximate the integral from 0 to 8. So let's draw our number line here. And see if you can find there's one conspicuous word that's left out of this description here. We are going from 0 to 8. Notice it never says the word equal. Let's see if they are equal. says the 4 subintervals given by the table. Well, it starts at 0, ends at 8. The next time we have is at 2, then 5, then 6. You don't have to draw these to scale. I just try to roughly just do that. So you can see in this case, notice the subintervals are not equal width, which is why they don't say the word equal. And if they don't say the word equal, you don't have to do that calculation to find the width of each subinterval because they're not equal. They're different widths. So let's calculate what this is. So we're going to take, remember the formula for the trapezoid. So 1/2 times the width times h sub 1 plus h sub 2, where the heights come from both endpoints. So let's calculate, in this case we've got 4 subintervals, so 4 trapezoids. So let's calculate each of these and add them up. So it'll be 1/2 the width of the first trapezoid, you can see, first subinterval I should say, first trapezoid. If you go 2 minus 0, you can see the width is 2. So 1/2 times 2. And the heights are going to come from both endpoints. In this case, our function is r, so r of 0 and r of 2 instead of f. So r of 0 plus r of 2. And then we'll write down the next trapezoid. The 1/2 times the width of the next subinterval from 2 to 5 is 3. You can just go 5 minus 2 is 3. You can see the width of that subinterval is 3. And the heights of that trapezoid come from the endpoints, r of 2 plus r of 5. And then the next trapezoid, 1/2 times the width of the next subinterval from 5 to 6 is just 1. And the heights come from r of 5 and r of 6. And then the width of the last subinterval from 6 to 8. The r of 6 plus r of 8. The width of this is 2. All right, so let's calculate what each of these are. So notice on the first one, the 1/2 and 2 reduce out, so we're just left with r of 0. Now this time, rather than looking at the graph like we did in those first examples, most commonly you're going to be looking at a table of values here to figure these out. So we know at time 0, r of 0 is 0, plus r of 2 is 5. So that gives us the area of our first trapezoid is 5. And now here they don't cancel out. So we'll have 3 halves. R of 2 is again 5 in the table. Plus R of 5 is 9. So here we can see we've got 14 divided by 2 is 7 times 3 gives us 21 for our next trapezoid. And then 1/2 times 1, well that doesn't cancel out, we're left with 1/2. R of 5 we know is 9, plus R of 6 is 10, gives you, well this time it doesn't reduce at all, 19 times a half, so that'd be 19 halves. You don't always get integers out of these. And then 1/2 times 2, here they reduce out again, and gives you R of 6 is 10, plus R of 8 is 11, giving you 21. So if we add these all up, let's actually convert them all to halves here. So if we add up the integers first, 21 and 21 is 42 plus 5 is 47 plus 19 halves. Let's get a common denominator of 2, so the 47 is 94 halves plus 19 halves gives you 613, so 113 halves. Okay, so that's our approximation of that definite interval, 113 over 2. And now it says, does this approximation overestimate or underestimate the actual value of this? Give a reason for your answer, in other words, justify. So we use the trapezoidal method. Remember, we just figured out the trapezoidal method, it depends on the second root, whether the graph is concave up or concave down. And normally we wouldn't know for sure, even if we sketch these points, we wouldn't necessarily know for sure what's happening between the points to see whether the whole graph is concave up or concave down. We'd see whether it could be. But notice what they tell us right here, the second derivative is less than 0. So if you forget which way it goes, just sketch a graph. Okay, so we know it's concave down. Shaped like the front, so just draw something concave down, and then just draw a trapezoid on any subinterval there. This is how I remember it. You see, oh yeah, the trapezoidal method, if it's concave, I'm definitely going to underestimate. It's going to miss that section. So that's the way you can remember just by drawing a little picture of what it's going to look like. So we can say this approximation here, 113 over 2, underestimates the actual value of integral from 0 to 8 r of t dt. And then to give a reason for answer, it'd be since r double prime of t is less than 0. That should tell us here. All right, let's take a look at part B on the same problem here. So this time though, it's a different method. It says use a right Riemann sum, so we're using rectangles this time, with the 4 subintervals given by the table to approximate. Notice what approximate is a little bit different. It's got a 1/8 out in front. And then using correct units, explain the meaning of this. So let's draw our number line again. Again, notice it doesn't say the word equal here. But this time, when it's a Riemann sum, a Riemann means rectangles. So we're just going to do width times height. So draw our number line here. 0 to 2, 2 to 5, 5 to 6, and 6 to 8. Now notice what we're approximating. We'll talk about why that's there in just a second here. Well, we've got a 1/8 out in front. So an easy thing to forget is that 1/8. So you don't forget it, we're going to put it at the very beginning. Big old parentheses. And then we'll do the width times the height of each of these rectangles. Okay? So the width of the first one you can see is 2. Times the height using a right Riemann sum. The right endpoint on the subinterval from 0 to 2 is 2, so that's going to come from r of 2. Plus, the width of the second subinterval from 2 to 5 is 3, times the height comes from its right endpoint, which is the 5. On the subinterval from 2 to 5, 5 is the right endpoint, so the r of 5. Plus, the width of the next interval from 5 to 6 is 1, times the height comes from r of the right endpoint is 6, plus the width of the last subinterval from 6 to 8 is 2, times the height comes from the right endpoint of r of 8. So you got 1/8. And then 2 times r of 2, you can see in the table is 5, plus 3 times r of 5 is 9, plus 1 times r of 6 is 10, plus 2 times r of 8 is 11, 1/8 we've got 10 plus 27 plus 10 plus 22. Add those up and multiply by 1/8. Gives you 69/8 is our approximation for this definite integral with the 1/8 out front. But now let's think about why would that 1/8 be out there when it says explain the meaning of this in terms of the number of raffle tickets. Okay, so we're putting it in the context of the problem. Well, when you have that out in front, whenever you see that, it's because it's coming from this formula, 1 over b minus a, integral from a to b, whatever function is in this case, r of t with fx. And remember what this is the average value formula. So, you can see they're just simplifying 8 minus 0 is just 8. So that's how we're going to explain the meaning of this. So we've got the 1/8 integral from 0 to 8 r of t dt is the average. Now what is it the average of? Well, remember this formula is the average of whatever r of t represents. In this case, r of t represents the number of raffle tickets sold. Okay. So the average number of raffle tickets sold that says using correct units. But if we just said that, that wouldn't be correct. Because notice it says R of t is in hundreds of tickets, and there's our units. So each of these actually represents in hundreds. In hundreds of tickets. And there's one more thing we have to reference when we're explaining the meaning of this, and that's the time interval here. Normally you could just say from t equals 0 hours to t equals 8 hours. But here they actually tell you what those represent in the context of the day. They tell you t equals 0 is noon and t equals 8 is 8 p.m. So you can say more specifically on this problem from noon to 8 p.m. Take a look at another example with some different parts here. So sometimes they organize the table as horizontally, sometimes vertically. So this is the vertical table. So it says this one during the time interval 0 to 12 hours, water is pumped into a swimming pool at the rate P of t cubic feet per hour. The table below, there's a table gives values of P of t as strictly monotonic differentiable function for selected values of t. All right. So part A is just explaining the meaning of some things. Using correct units, explain the meaning of integral from 0 to 12 p of t dt, and then with a 1/12 out front. So we already saw in this one, when it's a 1/12, that's going to represent the average value of whatever function's in here. But what if it doesn't have the 1/12 out front? Now, so again, we're putting it in the context of the problem in terms of water in the swimming pool. Well, if it doesn't have a 1/12 and P of t is a derivative, which it is, a couple clues they tell you, rate, another word for the derivative, rate of change, and look at the units. Whenever it's something per something, that's a derivative too. So when you have a definite integral of a derivative, remember what it represents is the change. It's like those initial plus change problems, but there is no initial, just the change. So that's how we're going to explain the meaning of it in the context of the problem. We'll say this integral, the definite integral from 0 to 12, P of t dt, is the change. Now, what is it the change in? Well, it depends on what P of t is the derivative of. P of t represents the rate water is being pumped into the swimming pool. And look at the units, cubic feet per hour. So if it's in cubic feet per hour and you integrate that, think about with like units, what happens here. If you go from, it's kind of similar to how you go from, if you go from position to velocity to acceleration. Well, position's in terms of meters, right? Or something like that, some kind of distance-wise. And velocity could be meters per some time unit like seconds, and acceleration is meters per second squared. So you take the derivative going this way, you notice you keep dividing by the time unit each way you go. But when you integrate, it goes the other direction. Each time it gets rid of one of those time units on the denominator. So if we go from P of t and we integrate that, and P of t is cubic feet per hour, notice it's going to get rid of that per hour. Just like when you go from velocity to position, it gets rid of the per second. So that tells you the units and what it represents. If it's just cubic feet, well, what's in terms of cubic feet? Well, that's the volume. So P of t is the change in the volume of water in the swimming pool. And the units would be in just cubic feet. We either write it this way or write out cubic feet. But again, you have to reference the interval from, in this case, they don't tell us the context of day it happens in, so we can just say from t equals 0 hours to t equals 12 hours. So it's the change without the initial, because it doesn't tell us how much water started in the swimming pool. Right? If we knew that, then we would know exactly how much is in the swimming pool. This is just how much it changes by. So if we knew, let's say there were 100 cubic feet of water in the swimming pool to start with, that would be the initial plus this definite will represent the change, how much it changes by on the time interval from 0 to 12 hours. All right, now let's take a look at explaining the meaning of this other one, or I know it's there. This is similar to the last one we did in the last problem. Well, if you have a 1/12 out in front, now it represents the average. So this, it's not just the change, it's the average, is the average. And what is it the average of? Well, it's the average of whatever function we're integrating. So what does P of t represent? Well, it says P of t, the units are in cubic feet per hour, and it says the water pumped into the swimming pool at the rate. So it's the rate water is being pumped into the swimming pool. Okay. So it's the average rate water is being pumped into the swimming pool. Again, let's put the units right here in. Well, whenever you're doing the average, the units always stay the same. So it's going to be in cubic feet per hour. You can write it out that way or write it out this way. Either way, the same thing. The other way to see why that is, remember we saw this one would be in just cubic feet, right? When we integrate. But once you put the 1/12 out there, that 12 minus 0 comes from here, right? And that's in terms of time. So when you integrate this, it goes back to cubic feet. But then this is per hour. It comes right back in when you have that 1/b minus a out front. So because of that 1/b minus a, the units will always end up staying the same as whatever the original function's units are. And again, you just have to reference the interval from t equals 0 hours to t equals 12 hours. Okay, so that was just explaining the meaning of these. Now we're going to actually do some approximations here. Part B says use a midpoint Riemann sum. So again, we're just dealing with rectangles. With times height. But this time it says 3 subintervals of equal length. So this time they are equal to approximate this integral from 0 to 12. show the computations of the linear answer. All right. So let's figure out the width of each subinterval. Remember the calculation we did there? This time they are equal, so the width of equal subintervals. Or what we do is we first take the width of this whole subinterval, which comes from the lower and upper limits of your definite interval. So it'd be 12 minus 0 is the width of the whole zero, divided by how many subintervals we're using, in this case, 3. That gives you 12 divided by 3, so 4. So 4 is the width of each subinterval. So use that to draw our number line. So we're going from 0 to 12 by 4s. 0, 4, 8, and 12. So even though you have the table, always draw the number line. It's much easier to figure out. All right, so we know the width is 4, so we can put that down of each one. Yeah, we're just doing the width times height. We just have 3 rectangles here, really. And to get the heights, they come from the midpoints. And our function here is p, so it'd be p of, well, the midpoint of the first subinterval is 2. So for width times the height, 4 times p of 2, plus the width again is 4, times the height comes to the midpoint from 4 to 8 is 6. So p of 6, plus the width from 8 to 12, again they're all 4 here, and the midpoint is p of 10. And then we can put those in. So p of 2, let's see, our table is 12. P of 6 is 25. P of 10 is 50. So we get 4 times 12, 48, plus 100, plus 200. Gives you 348. And it says show the computations that lead to your answer. That's what we did right here. So we don't want you to just do it all in your head and get 348. Now we don't have to, but because we did part A, we know what the units are, right? This was the change in the volume of the swimming pool, so it's in cubic feet. So our estimate is, that's how much the volume of the water in the swimming pool changed from 0 to 12 is by 348 cubic feet. And we didn't have to put the answer, it didn't say you had to, but that's what we did. Then the final part of this one, part C. Now we're going to use a left Riemann sum. So again, rectangles, width times height. All the Riemann sums are rectangles. But this time, notice, don't assume just because it's the same problem, you're going to use the same subinterval. This one says 6 subintervals. They are equal, but there's 6 of them instead of just 3. And notice what we're approximating has the 112 dot from. So, to calculate the width of equal subintervals this time, and you only do this if they're equal. The first problem we did was not. But the problem we did right before this, I should say. Take the width of the whole subinterval, which is 12 minus 0, divided by the number of subintervals this time is 6. That gives you 12 divided by 6 is 2. So this time, the width of each subinterval is 2, so let's draw our number line here. This time we'll go by 2s. Starting at 0, stopping at 12. So 0, 2, 4, 6, 8, 10. Alright, so there's our 6 subintervals this time. And this time, don't forget that 112 out in front. Let's put that on front of the whole thing with a big old parentheses here. And then the width of each subinterval is 2. So we've got 2 times, this time we're using the left Riemann sum, so the left endpoint I'm using would be 0. So 2 times our function here is p, so p of 0, plus 2 times the left endpoint on the next subinterval from 2 to 4 is 2. It's p of 2, plus the width of all of them again is 2 times width of the next subinterval from 4 to 6 is p of 4, plus 2 times p of 6 is the next left endpoint, plus 2 is the width again, times P of 8 is the next left endpoint, plus 2 times the last on the last subinterval from 10 to 12, the left endpoint is 10, so 2 times P of 10. Now we could just plug these in and calculate the way we normally do, but because we've got equal subintervals, there's something you could do to make your calculations a little simpler if you want. You don't have to. But notice all these, because they have equal width, all have a 2 that we can actually factor out. And 2 times 1/12 reduces to 1/6. Again, that's an optional step just to make our calculations a little easier. And once we factor out the 2, all we're left with is P of 0 plus P of 2 plus P of 4 plus P of 6 plus P of 8 plus P of 10, which we can get from the table. P of 0 is 0. P of 2 is 12, P of 4 is 20, P of 6 is 25, P of 8 is 30, and P of 10 is 50. So let's look at what those work out to be. We've got 1/6. If you add those up, let's see, that gives you, let's see, there's 100 right there. We take those 3, and then that's 37, so 137. And that does not reduce it, okay. So you have 137 over 6. And we don't have to put the units, but this would be in, it's the average, so let's say it's cubic feet per hour. So we showed the computation to let our answer, but this one also asks, does this approximation over-approximate or under-approximate the actual value? Justify our answer. So this time, it was a left Riemann sum. Remember what we said about that? That depends on whether the function is increasing or decreasing. The way we can tell on this one, well, if you just look at these values, 0, 12, 20, 25, 30, 55, 55, those are increasing, right? But how do we know it doesn't decrease somewhere between? Well, we normally wouldn't, except for one key phrase that says the function is strictly monotonic. Remember what that means is it's either always increasing or always decreasing. In this case, it's always increasing. So if you draw a graph, even if you just draw a straight line, it's always increasing like that. And use a left Riemann sum, you can see that's going to underestimate. So we can say 137 over 6 underestimates the actual value of the 1/12 integral from 0 to 12 p of t dt. And then the justification would be, since our first derivative, since the function's increasing, we know p prime of t, first derivative would have to be greater than 0. And that concludes the notes for AP Calculus on approximating definite integrals using the Riemann sums and trapezoidal sums.